ready. Maybe we can start. Floor is yours.
Good morning. We are continuing our course on quantum transport, and as usual, I will remind you what we did last time, what was the outcome. So last time we discussed quantum corrections to conductivity. Quantum correction to conductivity. So first of all, there is a conductivity sigma 0 classical one, which is p squared u times p, and if we take spin into account, it has next factor of 2, and the correction to this conductivity was negative, and it was e squared over 2 pi squared h times the logarithm of the system size. And since we have spin, it has another 2 here. And this situation, we said it's called the orthogonal case, and it corresponds to a system where spin is conserved. Spin conserved. And there was another situation where spin symmetry is broken, and there sigma 0 is the same, and delta sigma is positive, and plus, and there is no spin down in here, it's just because h the same log. This situation is called symplectic. And here spin symmetry is violent. First case, second case, and then there was the third case where delta sigma is 0. And this happens when time reversal symmetry is broken and there are no equivalents in the system. And this case is called unity. Then for these three cases, it's all in 2 dimensions. For these three cases, we have the beta function, beta of, I can also call it sigma, because in 2 dimensions, sigma and g and conductor is the same function of the logarithm of sigma. Goes like this, or like this, or like this. So, in an entire limit, when sigma is large, there is this quantum correction, which is either positive, negative for the first case, positive for the symplectic case, or as I said, it is 0 the unitary case, but actually it is not 0, it is minus, there is some negative part, but it's smaller than these two. We did not perform the calculation up to this accuracy, so it's negative, but much smaller than this one. This middle line is unitary. This middle line here. And the interesting observation here is that in the symplectic case, we do have metal-insulator transition in 2 dimensions. There is a critical point. While for the other 2 cases, there is no transition and the system is always insulated. At all values of sigma, this function is negative. Just to remind, this is the derivative of sigma over log big. Yeah, and then we started another topic, which was also about quantum correction to the diffusion equation or diffusion propagator, and there we had the following thing. We have a set of diagrams where there is a classical diffusion propagator, which is called D0, and which equals 1 over 2 pi nu tau squared, dq squared minus I omega. It is this ladder, and then there are corrections that have the form of some vertex gamma inserted here. This two particle vertex plus it can be inserted twice, 3 times, and so on. And the full diffusion propagator is the same as this D0, 2 pi nu tau squared, dq squared minus omega, minus gamma. So this gamma, this vertex, is sum of the geometric series. It ends up in the denominator, and for this vertex gamma, it was an expression. It's a box that is with a Cooperon loop going on. This is Cooperon ladder. And this thing equals integral over two-dimensional momentum capital Q over 2 pi squared. Product of two things. The gamma box, which depends on capital Q, small q, and omega, times the Cooper of this loop, which depends on capital Q. And this Cooper on the node is exactly the same as the diffuser. It's exactly this expression. 1 over 2 pi nu tau squared d squared minus d, sorry. This is capital Q here. Minus omega. And the interesting thing is this Hikage box, which is these four ring functions here. So Hikage box H is the sum of two contributions. One contains four ring functions with small momentum Q going this way and momentum capital Q going this way. Plus the same box with single impurity line inserted either this way or the opposite. These functions are target and opposite. Target and opposite. So this part we call H0, these two things we call H1. And there was a homework to compute what these things are. So, who succeeded? Anton? It's pretty normal situation. So H0, it's an integral over momentum P for the product of four green functions, which can be calculated the same way as we always so far integrated any green functions, just by writing the momentum integral as the integral for psi and taking the residue at the pole. So what should I do? Should I just show you the answer, or should I show how to calculate it?
The whole
Hmm?
the whole
The whole, we'll need Okay, let me do it this way. I can calculate these two things, assuming that all external momenta and frequency are zero. Then it is just a number. This is a number, this is a number. And then there are corrections to this number if we expand in small values of q, this q and omega, and
Sorry, before we go too deep into calculations, why is this actually just a Cooperon? I mean, it has a self-crossing, right?
yeah.
And why don't it bother us?
Imagine
Why
this
should it
picture in
bother us?
3D. Imagine this picture in 3D.
Okay,
It's a,
yes,
it's a
it is
just-
still a Cooperon. Okay, yes. yeah,
No,
okay.
actually, it is a Cooperon because the arrows point in the same direction. That's the only.
Okay. Yes, okay. It probably doesn't. Okay, okay.
Well, so if all external momenta are zero, and if frequency is zero, so this is the coming box of q equals omega equals zero. This is just an integral mu d psi over all momenta. And then we have two retarded functions and two advanced functions, all taken at the same momentum. So it is epsilon minus psi minus I over 2 tau squared, two retarded functions, and epsilon minus psi minus I over 2 tau squared, two advanced integrals. This is a number. Yeah. It's a very simple integral, and it equals 4 pi mu tau squared. Sorry, tau cubed. This is mu here, and all the rest is only tau inside, so it should be tau to the proper power. It's just very simple number. And h1, these two things in the same limit, h1, when everything is zero, is, first of all, it's a factor of 2, because we have two such diagrams, they actually equal. Then there is one impurity line inside, which means 2 pi mu tau in the denominator. And then there are two integrals. Let me put it here, retarded, advanced, retarded, advanced. So we have one momentum inside this loop, so it's P, and another momentum inside this loop, so it's P prime. Which I don't know why, but let's consider we prefer that. So there's all two, it's just one. And these two integrals, here and here, are exactly the same. This integral contains two advanced functions and one retarded. This one also contains two advanced functions and one retarded. So this is an integral, mu d psi. Just this denominator here is epsilon minus psi plus, sorry, yes, plus I over 2 tau is the retarded function. And the other one is epsilon minus psi minus I over 2 tau squared. This is two advanced functions. This is one part. And then this integral is squared, because we have two such boxes. And the integration inside each box is independent. And then there is another diagonal like this, and it's exactly the same, but it contains two retarded functions and one advanced in each integral. So it adds here the complex conjugate. Well, but actually, as far as I remember, this thing will be real anyway, so this adding complex conjugate will just multiply by 2. Now somebody tell me what the result is. It doesn't require any calculation. Anybody? Zero. squared, you really think it can be 0 because it's squared here. Okay, the answer is 4 pi nu tau u minus. It's minus the first one. Well, actually, this integral is completely purely imaginary. We have a pole here, and then the square root becomes negative, and the second one is also negative. So this is a very important observation, which tells us that whenever all these external momenta and frequency are 0, adding these three things gives exactly 0. This is why we now have to compute corrections to these numbers, taking into account that Q and omega are not zero. They are small, but not 0, and there are some corrections, and this calculation I will not do on the board. It was your homework. So the full result, H0 equals 4 pi nu tau cube times 1. This is the part that there is a 0 momentum of frequency, and then minus tau d small q squared minus tau d capital Q squared plus 3I omega tau. And so on. So this is an expansion in small momenta and small frequency up to the linear order in this one and to quadratic order in this one. You can expand further, but further terms we don't need them. Any question? No? No. H1 is 4 pi nu tau q, and the first one here is minus 1, the one that is 0 frequency of momentum. They should be 2 cancel each other, and then plus 2 tau d small q squared, 2 tau d large q squared, minus 4 pi omega tau. Yeah.
So, could you explain where you took it from?
So that's integral. For example, for frequency, it's easy. So if you have frequency omega, and here it means that retarded functions and advanced functions don't have the same energy, they have energy difference omega, so you add omega here in the denominator. Then you take the same residue and you get the result, which looks like this, and then it will be 1 over 1 minus 3I omega tau. So this is how it changes. If you, then you expand, you say omega tau is small, you expand, and you get this 1 plus 3I omega tau. With momentum, it's a bit more complicated, so you have to insert momentum Q should go along these lines, momentum capital Q along that lines, so you will have 4 terms in the denominator, and psi will be a little bit shifted. And then you will get here also plus something dependent on Q, which will, this calculation is exactly the same, is done exactly the same way as we previously computed a single step in the diffusion. It was just 2 green functions, with also with 1 omega and 1 q. And we did exactly the same. We had 2 denominators, we integrated over cosine, and then we expanded to small omega and q. So I'm just not doing it explicitly here because this calculation itself is quite lengthy, but it's very simple. I mean, there's no any. You don't need to think, you just do it. It's not something that requires a lot of mind effort. Okay, so if this part is understood, is it understood? Yes. The total cannibals, which is the sum of these two. We cancel the 0 over the product, and the result is 4 pi nu tau to the power of 4. This is very simple. D small q squared plus d capital Q squared minus I. So that is cancelled. 2 minus 1 is 1. 2 minus 1 is 1. Minus 4 plus 3 is minus 1. So this is very important. The cancellation of this leading term is extremely important. This cannibals, this object, is 0 at 0 frequency and 0 momentum. This is a manifestation of what?
Conservation of
Conservation of density. Yeah, we will see in a moment how this comes about. So far, so we have for our vertex gamma here, we have a Cooperon, and we have H this one, and we need to compute the integral over capital Q, and this will give us the final result gamma. Gamma integral over capital Q d to capital Q over 2 pi squared. So what happens if I multiply this h times that c? Well, I have 2 tau squared. This 4 pi nu tau power 4 cancels partly against 2 pi nu tau squared from the Cooperon. So what is left is 2 tau squared. And then there is a fraction. And the fraction is d q squared plus dq squared minus I omega divided by dq squared minus I omega. And since I'm writing this on the board, not on the paper, I can erase them to the right. You can also. So I represent the same fraction as d small q squared over d capital Q squared minus omega plus 1. It's the same thing. So who can tell me what the value of the Q term is?
Diverges.
Yeah. And why it diverges?
because of one.
Because of one.
Okay.
When Q is large, this thing is small, so actually it's logarithmic. It must be small, but this one is 1, so then it diverges. And this is not what we expect, because we wanted some correction of this. Something that we can discuss, and this is simply infinite.
Probably we'll again need the imaginary part.
No.
We lost some contribution apparently.
Does anybody know what went wrong with this calculation?
We initially assume that QD is small.
This one?
Yeah.
Yeah, it means that we have some cutoff. Yeah, you're right. It's not formally, it will not diverge, but it will be very large. It's too large. Okay, I'll just tell you. In these diagrams that we plot for gamma, for H, for C, there is some extra contribution that we erroneously included. And this extra contribution is H0, the empty part without any dash line inside, times Cooperon is the ladder. 1 impurity plus 2 plus 3 plus 4 times just single impurity. So the first term from this Cooperon series. So this object looks like this. This is the box. And this is a single impurity. And it should not be included into gamma, because if you insert gamma like this, it's not a correction. I mean, we have diffusion, gamma, diffusion, gamma. If gamma is just a single impurity line, and we insert it there, we just have the same diffusion twice.
Yes. Ah, you mean this is the extra term that we included actually, but we should not.
So this extra thing,
Yes,
which
okay.
was
Okay.
quite, which should not have been there, is H0, which is 4 pi mu tau cube. 4 pi mu tau cube. And the single impurity line is 2 pi mu tau. This is exactly 2 tau squared.
There's a problem with arrows because you said impurity between retarded and advanced.
Yes,
Yeah, right.
but it's the same, it's just flipped.
Yeah.
So actually what happens, we have many diagrams inside this gamma, and there are diagrams with 1 impurity line, 2 impurity lines, 3 impurity lines, and many impurity lines, and we should start from 2 lines. We should not include gamma, which contains only a single impurity, because it does nothing to this diffusion method. So this thing that we included by mistake is 2 tau squared, which is exactly this one here. It's 2 tau squared. So if I exclude this thing, I just drop this unit from it. Please raise the hand, anybody who did understand what I just said. Now please, those who raised the hand, put it down, and those who didn't, raise it. Okay, so who should I take from you?
Yeah.
What exactly was not here?
I thought you share why we must not do that.
Okay, let me draw it. So, we have a diffusion which goes like this. Then we should include something, and if we include just this part here, it will, I can draw it in another way. Then I can draw it like this with single impurity line, and then the diffusion continues. So if I now flip this thing back, it's actually the same as a single diffusion. So this should not be a part of this thing, it is actually a part of this thing. It was already there. And the next, for example, the next diagram, which has 2 impurity lines inside Cooperon, it will look like this. It's the ladder, and then there are 2 cross lines, and then it continues. This is not part of the original. And if you take H1 and the Cooperon with a single line, it will be a diagram like this. Because of those, then there is a single impurity line, which is covered by another. So this lines up, this is retarded, this is advanced. This line on top connects to retarded functions. It's the line that crosses the chemicals. And the one line inside is the one from the. So for this diagram of H1, Cooperon starts with a single impurity, and for the empty chemicals for H0, Cooperon should start with 2 impurities. Should not start with 1. And actually, it's a very simple check. I told you on the very first lecture that the diffusion propagator, this one, T0, is singular when Q and omega are 0. It has 0 in the denominator, it diverges. This is a manifestation of the conservation of number of particles. But now, when I include this correction, I also have gamma in the denominator. happens to this gamma when Q and omega are 0? Now, when it has this 1, it remains finite. It does not vanish. Now, when this 1 is removed, when Q is 0, it will be 0. So it will not violate the conservation of the number of particles. And with this 1 inside, it would violate. So, if this part is relatively clear, now somebody please tell me what the integration of the cube is, of the capital is. Is it
Logarithmic divergence.
logarithmic divergence? This is true. So we have tau squared here, right? We have dq squared here, and we have another d in the denominator. So what we obtain in the end is tau squared, q squared divided by pi comes over here, times the logarithm of a over a. Actually, this integral should be limited from above by the inverse mean-free path, from below by the inverse system size. Exactly the same as it was for quantitative. Yes.
Some question. When we calculate this Hitani box, should be expanded over the Q, big Q, right? So it's like a small parameter tau dq squared. And now when Q is on the upper limit, it's not very small, right? It's order of 1.
Yeah, exactly.
And
This,
so
this is exactly the reason why this upper limit is like this.
yeah, but why it's still like correct if it's not small on this limit?
This is exactly. So what you say is very true, and this is exactly this. Your statement is exactly the reason why this limit is put here. So for any smaller q's, what we did was correct. And when q becomes large, it becomes compared to this, our approximation doesn't work anymore. So we are not allowed to integrate larger q's.
But actually we need to take like much smaller than this value, right? So
Yeah,
that would be truly correct, but because it's logarithmic, we
Because
don't
it's logarithmic, we don't really care for exactly.
And why we suppose that this other part of integral that we throw out, it doesn't have any divergences and was
Well,
it is
actually-
much smaller than this.
Actually, you can do this whole calculation without assuming that q times a is small, and you will see that above this limit, it starts decaying much faster. So it's logarithmic, and then it decays faster.
Okay.
It's just,
Cannot move faster than diffusion on the bridge.
yeah, it's called a realistic
Okay.
limit, and but the expression itself is much more. So we are lucky we can use this approximation because we have this logarithmic term and we don't need more accurate result. So this gamma is written here. Now what will happen if I insert this gamma that dominates up there? I will get new corrected diffusion propagator, which looks like this 1 over 2 pi mu tau squared dq squared minus minus this. Minus. I have tau squared q squared here, tau squared I take out, so I have minus q squared over 2 pi mu. Great. One x I times the logarithm. Yeah. Both coefficients are correct. And this term actually looks like this term. They both scale as q squared. So what I have here is a correction to diffusion constant. There is a correction to the diffusion constant, supposed to be delta D, which is minus 1 over 2 pi squared mu logarithm a over a. And then, if there is a correction to the diffusion constant, there is a correction to conductivity, because conductivity there is an Einstein relation d squared mu d. So if this d requires a correction, conductivity also requires a correction. And is, I put delta here, d squared mu, minus d squared, 2 pi squared, logarithm a over a, and it is exactly the same as in the very first line up to the spin factor.
What about the speeds?
Sorry?
I have three different cases for conductivity. It depends on its structure.
This is spin. And this is spin. But in this population of the diffusion, there's no spin. So if you like, you can, or if you like, you should say that the Einstein relation sigma equals 2 squared mu d, 2 due to spin, and then you will have this spin. Yeah, that's right problem. So this density of states, mu which stays here, this density of states takes into account only one spin component. If you have 2 spin components, you should double the density. This has nothing to do with the diffusion constant. Okay, so to summarize, there are 2 alternative calculations. One is the calculation of conductivity and the quantum correction to conductivity. The other one is the calculation of the diffusion propagator and correction to the diffusion propagator. And these 2 corrections are actually related by the Einstein relation the same way as the Baer-Drude conductivity is related to Baer-Drude, so just Baer diffusion constant by the same Einstein relation. So we just did 2 alternative calculations of the same quantum correction. This quantum correction can be thought of as a correction to conductivity or as a correction to the diffusion constant. It's just the same correction. And yeah, please ask some questions. Otherwise, I will think that you didn't understand anything, and we'll start from the very beginning once again.
We calculated the corrections. We were the heroes, right?
So, no questions to do this part? Well, very good. So what does this quantum correction business, what does it teach us? What can we learn from this?
Okay, actually, questions. So all what we've done, we did for free electrons, right? I mean, no interactions.
No interaction.
Okay. So, and if we include, I don't know, Coulomb interaction, which is always here, it will screw everything completely, or?
As was suggested by Professor Nazarov.
Can you just repeat the question? What?
Yeah, the question was what can we change if we include interaction, Coulomb interaction. The answer is what was given by Yuri Nazarov in one of his previous lectures, that these are not electrons, these are quasi-electrons, and they do not interact. But actually they do weakly interact, and it will modify something here. You can also compute corrections due to interaction. They will provide also corrections of a similar form.
I mean, but they will be corrections.
They will be corrections.
Okay.
Okay. Don't they just provide a cutoff for those logarithms, like elastic time, whatever? Like instead of L, I plug in elastic
They
scattering time.
do provide a cutoff for Cooperon, but not for diffusion. So Cooperon requires tau phi data phase rate here. Diffusion does not, okay? Because interaction does not violate conservation of the number of particles. And also there is a correction to conductivity, which is not the correction to the diffusion constant, which is actually the Schroeder-Randolph correction to the test states due to interaction, and it is actually similar to this at the same order, but for Coulomb interaction. For spring Coulomb, it's much smaller.
So it means that for diffusion, integrals involving diffusion, I'll still have to cut those at system size from above, and then, I mean, or from below in terms of momentum. And for couperons, I can insert the phase theta instead, right?
You insert which one is smaller.
For couperon, yes, but for diffusion, no.
Diffusion, yeah, but this is couperon.
Yes, I'm just.
Yeah, diffusion is different. It doesn't have the phase.
Okay.
Yeah.
Just to recap, what kind of diagrams have been omitted for the activity and for the other?
The Romo diagrams. Of course, this is just a leading correction. For example, in the unitary class, we have this result 0, and we have to include more diagrams to get something which is non-zero. And I will discuss this on the next lecture.
Yeah, could you explain the reasoning behind why we can approximately get interactions for the cosines?
Well, this is not actually the topic of my lecture. It's the essence of thermodynamic theory. When you have metal with many electrons which strongly interact, say Coulomb interaction or some other type of interaction, you can actually renormalize this model such, so instead of considering electrons, you consider quasi-particles that live near the Fermi surface, and which is the effective description. It's like an electron with a cloud of, I don't know, whatever charge that is accumulated due to interaction, and it propagates like a cloud, and this quasi-particle is actually a free particle. You can say that it just propagates without considering interaction anymore. It can have a different mass and a different velocity due to this interaction, but otherwise these objects, they look like ideal Fermi gas. They do not interact, they just. The only thing you are not allowed to do, you should say that these things, they exist only at energies close to the Fermi energy. If you go far from the Fermi energy, then they do. It's an effective description, it's called quasi-particles, and it's a subject of a totally different course, another 10 lectures. Yep.
What is the insight of doing this calculation in different ways? What's the insight? What can you gain from doing this calculation in two ways?
Yeah, this was exactly the question I asked a minute ago. What can we learn from this calculation? I'm just about to answer this question. Unless somebody else knows. Yeah, so actually, in the very first lecture, we discussed what a single Green function is and what happens to it when we have disorder. What happens we have this imaginary part appearing, I on the 2 tau in the denominator, and it means that the actual Green function decays with time and the electron disappears very fast. Tau is a short time. Or if you look at it in the real space, it also means that the function decays if we do Fourier transform from momentum to space, decays on the length, which is the infra path. So the electron propagates and then very rapidly on the distance of infra path and on the time of infra time, it disappears. All electrons fast disappear. Actually, it does not disappear in reality, it just loses its momentum because it is scheduled. So it leaves the state at which it originally was. And it means that in a metal with many impurities, with diffusion, it's not correct to think in terms of electrons. Electrons are not well-defined objects. Well, they're well-defined objects in physics and reality, but when you think how the transport happens, you should not think in terms of electrons. You should rather think in terms of these strange objects, which are called diffusons. And I can draw some picture to explain this. I don't know where. So imagine you want to go from point A to point B. with point A, and there is somewhere else point B. And you want an electron to go from here and to end up there. You say, okay, and the electron, let's go. We have a momentum, velocity, we go, and then on the scale of the Winther path, this level disappears. What does it mean? It means that it encounters an impurity, and it is scattered, and it's not going to point B anymore, it's going in some random direction. But then it gets scattered in, and changes the direction again. And then it gets scattered in, and changes the direction again, and I can proceed for quite a long time, but in the end, hopefully it will arrive at the point. But some probability, there is a probability. And this thing is called what? It's called diffusion. It diffuses. But if we consider a single electron, it's a quantum wave. It's a wave with a wavelength, Fermi wavelength with a high frequency. So if I compute the amplitude, quantum amplitude for this process going from A to B, I have to multiply all these amplitudes. And this is a strongly oscillating function. It oscillates on a very short scale. And if I then average this object, average over all realizations of this order, of something rapid oscillating, I will get 0. So what I should do instead, I should not average the amplitude, but I should square the amplitude and then average. This is for quantum mechanics rules. If you have an amplitude for some process, you take the square, find the probability, and then you average. So the square of this amplitude means I should multiply it with the complex conjugate. And the complex conjugate of this amplitude is another amplitude which is going from B to A in reverse, like this. And this is exactly what diffusion does. It has two green functions, retarded and advanced, in opposite directions. It computes probability from going from one point to another. That's why this diffusion actually is propagator of the classical diffusion equation. Classical diffusion equation doesn't care about any oscillations on the, doesn't know that electrons are waves. It thinks electrons are just balls, then it's like billiard with obstacles. So the product of retarded and advanced function, actually both functions oscillate rapidly. When you multiply them, these oscillations cancel. This product is just a real function. It does not oscillate. But it's still the case. Yeah?
So when you said the electron disappears, you have this vanishing of the...
Disappears means just getting scattered. It changes its momentum, it does not disappear. We have different states in momentum space. Momentum 1, momentum 2, momentum 3. The electron in state momentum 1, then when it's scattered, it goes to some other state, momentum something else. So from the original state, it disappears. Actually, if you average over all possible states, it will disappear. Yeah.
Statistically speaking, that reverse is very low.
No, it's not time reversal, it's just complex conjugate.
So, the fact that we go back, not back in time, but go back on the same path is not statistically significant.
Very good points, I will answer right now. So actually, as I explained, any trajectory here, the amplitude of any trajectory is a highly oscillating function. You change anything, move a single impurity a little bit, or initial point a little bit, it changes completely. And the total amplitude from going from A to B is the sum over all possible trajectories. Then you have to take the absolute value square of this sum. But since each term is highly oscillating, it turns out that the main contribution comes from each term taken. So let me put it this way. The total probability is the sum over all trajectories, right? Sum over trajectories AI, and each trajectory has an amplitude. And then the probability will be the absolute value squared of the sum. Actually, and then we will average over statistical distribution. But since each term in the sum is rapidly oscillating function of parameters, this averaging actually means that we should take the sum of AI absolute value squared. So only the diagonal part of the sum is relevant. And this, if we do, it's an approximation, and this is exactly an approximation that takes you from quantum mechanics to classical. Classical description tells you what is the probability of each trajectory, and just sums the probabilities, not the amplitudes. And the probability of the trajectory is the absolute value squared, and is given by this diagonal. Diffusion, that's why diffusion corresponds to classical description in this terms. And more to this point, the quantum correction that we have computed is the deviation. So some correction of this result, so we take some other terms from this sum squared, which I will do it here. And I will also draw this picture. I will put it right here. So imagine now we have a diffusion, like we did that one, with the impurity lines, and then we have gamma inserted. Gamma inserted means this fan-shaped diagram of impurities, and then we continue. This is the target, this is the constant. We can represent what this means in real space in terms of these graphs. So we have some original point where we start. We have impurities, we're scattered, and we reach this point, this last impurity. So we have a diffusion, this double line, everything up to this point. But then on this last impurity, our return advance function goes to different impurities. So we have some set of other impurities, and we go like this with the target function, this, and say here, and with the advanced function we go in the opposite direction. We go first to this impurity, then to this one, then to this one, and levels. Such as this process. So there is a loop inside, and one of these two amplitudes, A, goes along this loop in one direction, and the A star, the complex conjugate amplitude, also goes in the opposite direction of this loop, and the interference of these two trajectories going one way or the other is exactly the quantum correction of the diffusion. So the probability to reach the final point has a correction due to this interference. This is what it's integral. Actually, this interference reduces the probability, so it slows down the diffusion. That's why we have a correction which is negative. The diffusion constant becomes negative. It means that this interference, these loops with interference, they are, actually it's a constructive interference that slows down propagation of the pipe.
And that we only have interference in the loops, we infer from the not cross. So
Only in the loops, then
that we only have interference within loops, we see from the fact that the loop is all out and the crosses is exactly the same.
not exactly like this. So we have, if we have just a single diffusion, a double line without any loops outside, this is constant, this we have proven, which is very simple. And this correction, this interference correction is only the leading corrections. There are others which are just smaller, But this is a leading correction because it also contains an almost classical object inside, which is the Cooper. So this correction has some oscillations which also are quite considerably cancelled because we have the advanced function between the same impurities. So Cooper actually it looks like the diffusion, yeah? I mean the propagator. Cooper is exactly the same form because we have time reversal symmetry. In the system, time reversal symmetry means that going around in one direction has the same amplitude as going in the time reverse direction. That's why these groups are important, because due to time reversal symmetry, this interference becomes stronger, because the phase is the same. So there are some lines which are misaligned here. This thing will oscillate and will average to something small, but the rest of the loop will not contribute in the extra smallness. It's only inside the handles. The smallness is only inside.
Then there could also be quantum corrections that are smaller on the original loop.
Yes, this is the topic of the next lecture.
Can you draw the leading diagram and the corresponding trajectory for the unitary case where I cannot draw Cooperons because they are suppressed?
Yes, I can. This will be on the next lecture. So far, we only consider. Yeah, sure.
And in real life cases, how these quantum corrections happen, and are there any examples when these quantum corrections become crucial?
Well, from a theoretical point of view, they are important because it's a logarithm, so they're actually quite big for the system. And for instance, in 2 dimensions, they tell us that any metal will eventually become an insulator. So there is no real metals in 2D. This is a very fundamental result. And if you like, for real life, for example, there is a notion of magnetic resistance in metals. So how the conductivity of a metal depends on magnetic field. Small fields, it's actually quite a profound dependence, which is completely due to these quantum corrections. This is called negative magnetic resistance. Well, it's known for like 40 years. This effect. Well, there are other effects which are maybe more subtle, which are not so easy to observe, but this negative magnetic resistance in dirty metals is always there. It's a direct manifestation of this quantum correction. So when you go to low temperatures and low and relatively large systems, this logarithm grows and this correction always becomes important. Yeah. So just to summarize, what we have computed so far is only the leading quantum corrections, not the final result. The conductivity is just a leading correction, and the leading correction contains only a single loop with the interference. You can include more loops, you can include more complicated Hikami boxes, and you will have further corrections which are smaller than this one. And there is a special theory to do this, and this will be the topic of all the remaining lectures to describe this theory. And this is just the perturbation result. Right? This is just leading the first order correction. First order quantum correction that deviates from classical physics. This is how quantum transport is different from classical transport due to these interference effects. And this is just the leading one of them. And also what we have seen, it's crucial that we have time reversal symmetry, otherwise delta sigma is 0. It's crucial to have this interference along the loop. And what we also see from here is that single electron process is not relevant. What is relevant are these double trajectories which compute either the diffusion with opposite errors or the Cooperon with the same errors, because these objects, they do not decay on the scale of mean-free path or on the time scale of mean-free time. They do not have mass. They have this singularity at Q and omega equals 0, which means that they can propagate to large distances and can survive for a long time. And that's the reason why we do it in terms, so this single function is ATK very fast, it has 1 tau here, and Cooperon doesn't have any mass in the diffuse zone. So it can propagate for the whole system size, and that's how you get the system size in the answer. Yeah.
How does it come about again that we have 0 and delta 0 without time reversal?
We just destroy this interference and going back and forth. If there is no time reversal symmetry, then the amplitude going this way and that way are not related to each other, and their product averages to 0. It's just a random number.
But why is it 0?
Well, look, the problem is that, okay, no, it's quite easy to explain. So the diffuse zone is the propagator where the target function goes one way, the advanced function goes the other way. And we did an explicit calculation for this on the first lecture. Now, for the Cooperon, we did not perform any explicit calculation. We just said that it equals the same ladder diagram when both arrows go in the same direction because we have a spectrum which is symmetric, because psi of phi was the same as psi of minus phi. So we can just reverse the arrow. But actually, this is just one particular case of time reversal symmetry. When you reverse time, the momentum changes. The direction with psi is the same, it means you do have this time reversal. If you violate this, then you go long way over time. And you have to compute Cooperon explicitly. You cannot just infer diffuse zone. When you do this for calculation, you will see that indeed it will require some extra terms in the denominator which will make it. But we didn't do this calculation. Well, actually, time reversal symmetry is not only about the spectrum. You can have some magnetic impurities that scatter different, that scatter such that you cannot reverse time. So these dashed lines can denote the same if you reverse the arrow or something else. Any violation of time reversal symmetry will make the Cooperon propagator decay. Okay, so let me make this statement one final time. The proper objects, how we should think about a disordered metal, is not in terms of electrons, it is in terms of these strange quasi-particles, if you like, that contain two electrons inside and that propagate as a pair. And there are two types of this. They are not real particles, it's just the way we should think of a disordered system. There are two types of them, one is the diffuse zone and the other one is Cooperon. And these imaginary quasi-particles, they can propagate, they do not decay with time or with distance, and they can also interact with each other, and Hikami box is exactly how they interact. So in this diagram here, which is gamma, you have a diffuse zone, which goes this way, and the Cooperon, which goes that way, and they interact with each other. This is interaction vertex. And this is just the simplest one. Now, if you would like to describe the disordered system in some better way, you should build a specific theory in terms of diffuse zones and Cooperons rather than in terms of electrons. And this theory should be an interaction theory. So it's not a theory of free particles, it's a theory of special particles with this type of dispersion relation, U squared, and with a specific type of interaction. For example, this is the interaction of diffuse zone and Cooperon. Just one diffuse zone and one Cooperon come together, interact, go out. This is the amplitude of the interaction. It depends on momentum and frequency. And this is just the simplest diagram. There are more complicated diagrams where you have more diffuse zones, more Cooperons. They interact more than once. They have more than one loop inside. You can do whatever you like with them. As long as you work in terms of diffuse zones and Cooperons, you can classify which corrections are larger and which corrections are smaller. And the smallest actually is contained inside the Hikami box. So each Hikami box means the correction you calculate will be smaller than the one with less number of Hikami boxes. Each loop also means that you have some small factor. So the more loops you have, the smaller is the correction. The leading one has only one loop, next to the corrections will have more loops. So there should be some effective field theory that describes these diffusons and couperons and how they interact, and if we know how to deal with, if we can derive this theory and if we know how to deal with it, how to solve it, we will more or less have not just the simple quantum correction, but maybe we can describe this whole curve, maybe we can prove that this scaling hypothesis is correct, maybe we can do many other things, maybe we can finally, as it's stated in the title of the lecture course, include some topological effects. So this specific theory, which describes a disordered system in terms of diffusons, couperons, and their interaction, is the non-linear sigma model. And after answering all the questions, I will proceed to introduce what it is. Please.
The question is very simple. You refer to the correction as like loop corrections, right? One loop correction, two loop correction. Where actually, how to actually see the loop itself? I mean, it is a figure of speech, but it should come. You mean from the up?
This is the loop. This is one loop.
Yes, and the next correction probably gives us the second one. Yes.
The next correction will contain two loops, and it will be on the, I believe, already not on the next lecture, but
yeah, okay.
next lecture.
Okay. Okay, thank you.
Yeah.
Isn't the upper loop in momentum space and the lower one in fluid space?
Yeah, it's one in moment. Well, this one is in real space, and that one is not in any space. It just topologically tells us which electron goes from which impurity to which impurity. I can deform this. It's just a diagram. It tells us how to multiply the functions. It does not tell us where exactly in real momentum space they are located.
Because it's already average.
This one is also, well, okay, right. That one is average. This one you have to average. So I have some explicit impurities, and then when average means you integrate all positions of these impurities. So in this sense, they are identical. And in real space, the dashed line in real space becomes a single point. It's called a function. It's this cross. And there, the dashed line has a length in the diagram. But I rearrange it such that they are very short. Originally, they were not very short. That's why that diagram almost looks like the one in the real space.
How do you know then that from like this logical diagram you get a new space? So what's the indicator?
It's just the order of impurities. One line goes impurities 1, 2, 3, 4. The other one goes in the opposite direction. 4, 3, 2, 1. One goes 1, 2, 3, 4. The other one goes 4, 3, 2, 1. Next loop. Okay, so I'm probably left with just 15 minutes, right?
Yes.
20 better than 15. And yeah, so forget everything we discussed so far. Just the introduction. And we are starting in kind of new topic, which was the original intent of this whole lecture course. And this new topic is called the non-linear sigma model. Non-linear, yeah. Non-linear sigma model. So this is the title, but actually the model itself we will not see today because it's still a very long way to reach it. So what I will tell you now is how we derive this nonlinear sigma model. And this derivation is quite lengthy. That's why we will not finish it today, but we will start. And nonlinear sigma model, as I already explained, is a theory that should tell us how the disordered system, disordered metal behaves in terms of different equilibriums. So we started actually with a single electron picture. We have an action, this is action, which describes single electrons and equals minus, I'll write a few equations, then I will explain what each element means. So I dagger epsilon minus psi of b minus b of r is the vectors plus omega over 2 lambda times phi integral over space t dr. This is the action. So somebody who knows how the field theory is described in physics, this is the action for non-interacting electrons. Phi is the electron field, and what we have here in brackets is actually energy minus the Hamiltonian. It's the action. Lagrange. It's not Lagrange. And they're non-interacting, which means that the action is a quadratic function in the field phi. But it's just a mathematical construction. It's just some fun. We have a field. Phi is a field. It's a function of point in space. It's like a wave function. It's a field, and this is an operator. This operator acts with the field, then we multiply it with another field from the right. Sorry, this is left from left. Then we integrate. So this is like a matrix element. And the only distinction why phi is a field and not a wave function is because phi can be anything. So field is an object that can take any value. So wave function usually solves the Schrödinger equation. So this is like a matrix element, diagonal matrix element with some random function phi. Yeah?
What is the omega over 2 lambda?
Omega is omega over here. And what is lambda, I will explain in a moment. So, there is one, but let's just do something like this. So then this for the action, and this action depends on phi, so it's a function. Phi is anything, or other objects fixed. With this action, we can actually define the green function. Green function, G, of the argument I will specify later. The green function is the integral. No, sorry, not the green. First we define this object Z, which is called a partition function. Partition function of any model is just, it's like a statistical sum of all possible states. It's the integral over all possible fields phi. Phi is the complex field, that's why it's phi star phi. Given it's the project of the exponent of minus the action. This is called Z, partition function. And this is the integral over all fields phi. It's actually a functional integral. So it's an integral of the value of phi at every point in space. It's infinitely many integrals. And once we know what this Z is, we can compute the green function.
So just for the sake of clarity, Z star and cross is the same, right?
Good point. Phi is actually a vector. It has several components. And star is complex conjugation, and that also takes transposition.
Okay.
So, green function green function G is the following thing. It's the same, it's I over Z over the partition function, the integral of the same fields, d phi star d phi. And then we have phi at point R1, phi star at point R2, and then the exponent notation. And this gives us the green function at points R1 and R2. So this may look complicated to anybody who sees this for the first time, but actually it's a very simple integral, although it's functional integral with the many integrations. The integral is Gaussian. It's the exponent of a quadratic function in phi, and this integral is the exponent of a quadratic function on phi and two extra phi's in front of the exponential. And any Gaussian integrals are actually easy to compute. You can think of it as a matrix. So this thing in the brackets, it's like a big matrix. It's an operator. It's an operator that acts on phi, but operator is just the same as a big matrix. So you can imagine it's a 2 by 2 matrix. No, it would be the same. Like 1 by 1 is easy. Whatever. It's an operator, and this z there, integral over exponent of a quadratic expression with some operator here is actually, who will tell you what it is? Who knows how to calculate Gaussian integrals? It's a determinant, right? It's just the determinant of this operator, determinant of whatever we have in square brackets. If it's a 2 by 2 matrix, it's a determinant of a 2 by 2 matrix. And what is this? What if you have two extra phi's? It's the inverse matrix. So if it's like, okay, it's the inverse matrix times the determinant, but we divide it by this, so determinant is cancelled. So what we have here is actually the same object in square brackets as an operator inverse. And this is exactly what we need for the green function. The green function is the inverse of the object in brackets. Yeah.
What is the rule of the green function here? So before we were talking about some differential equation.
As I said also in the very first lecture, we will think the green function as just the inverse operator, inverse of e minus Hamiltonian. And this is exactly what I have there in the exponent e minus Hamiltonian, and the inverse of it is exactly what this function.
So we go the other way around. We see that this is the inverse, then we go the function.
Originally, this inverse was called the green function, and what I did now, I just constructed an integral representation of this function.
The field phi doesn't field for
Thermodynamic. Here it is.
So this is cross.
Yeah. Well, actually, just mean that it's determinant, not inverted. But it will cancel anyway, so I don't care. Yeah.
Those are fermions for both.
Yes.
Sorry. But shouldn't be determinant in power -1?
That's the positive.
Okay, for most.
Okay, so this is just a way to represent the inverse operator in the form of a Gaussian integral. Nothing else. And now to the point which was asked in the beginning, what is this omega over 2 and what is lambda? So actually lambda is a matrix. Lambda is the following matrix: 1, 0, 0, minus 1. 2 by 2 matrix. It's either +1 or -1. And this structure is called RA, retarded or advanced. So it's a diagonal matrix. We have, in these square brackets, we have one diagonal term with epsilon plus omega over 2, and the other one with epsilon minus omega. And when we invert it, it's also a 2 by 2 matrix, and it has retarded function, one block and advanced function. So actually this one is GR here and GA here. It contains both green functions at once. And they are at different energies. This one at energy epsilon plus or equal to 2. This one at energy epsilon minus 2. So if we would like to build a diffusion of Cooperon, it will automatically be at the frequency omega. Yeah.
Phi is a two-component vector.
Phi is a two-component vector. Sorry? Electron retarded and electron advanced. It's again, phi has no physical meaning. It's just an integration variable. We presented it, the integral. So we introduced some variable, then we integrate it out. It does not exist anymore, so it doesn't need to have any physical meaning. But actually, you're right. All these field theories eventually acquire some physical meaning because we think of them in a certain way. And phi is electron, there are no positors. And we just introduced two different fields to generate retarded and advanced function from the same edge. That's why you can think of it as retarded field and advanced. And actually I should have added here also plus I0 lambda, so that the retarded function is plus I0 and advanced is minus I0. It's the part of this square.
Then I then miss the point. What is omega? Yes, I see, but I thought that there is some infinitesies. Okay.
Omega is just a parameter.
Okay.
Can be plus I0, can be
50
something finite.
hertz. Omega is
Yeah,
50
okay.
hertz. Omega is a number, epsilon is a number, everything here is a number. This is an operator. That one is a function of origin.
Then I understand. I think of a green function like electron at some point. Electron have a momentum and an energy.
Good point.
And here I have.
Good point. So let me finish with this. So I will let's little bit extend this thing here. So I have a green function which is between points R1 and R2, which depends on energy either plus or minus or equal to 2, which is either retarded or advanced. And in order to generate these two functions, I should take here these fields either the retarded component of them or advanced component. So field phi is a two-component vector, and I can put here the retarded part, and then I generate the retarded function at the energy epsilon plus omega over 2. Or I can put the advanced part of the field, and then I get the advanced function, energy epsilon minus omega over 2. And the momentum dependence actually is inside this number 2, just
Yes.
the transform to get the momentum.
Okay.
It's just the inverse operator.
Yes,
You can
yes,
invert in
I-
real space or momentum space. Or
I will ask my question later.
So this is the completely correct formula how the green function is expressed in terms of the integral. So once again, this is a field theory. This is an action there, but for now we did not think of any physical meaning of this field phi. We just construct an integral from nothing, such that we can represent a green function in forms in a form of such an integral. And yeah, if this thing is understood, the next thing we will do, we will average this green function over this operator, just as we did with diagrams. So we have to. So the average green function equals I over z, the same integral, average. Then there is a problem. It's not so easy to average because what is the object of average? Where is the random variable?
In potential and exponent.
Yeah. The random variable is this P of R, this zone potential, and it appears in the exponent here. But that's not a problem. The problem is that there is an object Z, which also contains this P inside, and then this Z in the denominator. And to average the ratio of two objects which are both fluctuating with disorder is not an easy task. even for Gaussian distribution, nobody knows how to evaluate the ratio to Gaussian. Or at least I don't know, maybe someone knows. So to overcome this obstacle, this denominator, there are many tricks invented by many profound scientists, and each way of doing this, there are several of them, each way has its advantages and disadvantages. Some are easier, some are more complicated. So I will use the simplest one, which also the least advanced one, which is called the replica formalism. So this is something that is called replica trick. Do you know, or if somebody knows about this, do you know who invented it? Replica trick. And in some form it actually was invented by Philip Anderson. So it's a very easy topic. If you ask any question, you just answer Philip Anderson, it's always correct. Metal oscillator position, also scaling theory of localization, replica trick. Everything is you to understand. So the trick is we introduce n is some number, n copies of our disordered system. And these n copies we call replicas. What does n copy? You have a piece of metal, and then you copy it with 2 pieces of metal, 2 identical, 3, 4, 5. The point is that the impurities out there placed in each of these copies are identical. These copies are just one-to-one copies without any distinction. Of course, it's in theory. In reality, you cannot have 2 samples with exactly the same impurities in them, but in theory, you can imagine n identical copies, and then we will say that now the action is the same as minus I integral phi dagger, epsilon minus Hamiltonian, times phi. And here we will have the sum over index A that goes from 1 to n, phi dagger A, and A. So the action is the sum of the action for each replica. In each replica will have its own field phi, but the Hamiltonian, the zone potential, everything is the same. So if these phi's would be the same, then the action would be just multiplied by n. And then this partition function, z, which is the integral over all phi's, this action is exactly the original z, the original one which we had in number, power n. So we just have n copies of our system. The partition function is the product of the partition functions. And since they are all identical, this product gives us nth power of z. And for the Green function, we write the same expression. I'm tired to rewrite every equation twice. So we will say that I have z power n here instead of z. And the field phi that we pick is taken from one particular replica. We compute the Green function. If we have many samples, we compute Green function with sample number 1, and we disregard all others. So these fields phi, the point R1 and R2, are taken from the sample number 1, from the replica number 1. So it's phi now has the index A, so I should say here A equals 1. And this is the same Green function, doesn't change it. So the only thing changes now is z to power n instead of z. And now if I want to average this Green function, I can do this. But I'm concerned, this identity is true for any number n. whatever n is, this is the green function. So it's yeah, I'm moving. So this green function is given by this expression no matter what n is, even before I average it. So I have n replicas, I take the fields from the first one, this is the green function. So since it does not depend on n, I can as well take the limit n goes to 0. And then it will kill this power n denominator, and then this function can be averaged. At this very interesting point, I will stop in today's lecture and please ask any final questions.
I just missed why it doesn't have
Please not.
but why it doesn't have
You have n copies of the number 1, of the number 2, and so on, of the number n. N times identical system. You compute the green function of our code going from point 1 to point 2 inside the sample number 1. This result does not know how many other copies you have, it does not depend on n. It means that we will do all the calculations with some n without specifying it, we'll get some result, and then in this result we will take the limit n to 0. Well, if you have one sample, it's 1, but since the result, the green function does not actually depend on n, okay. Yeah.
So we chose to use replica trick. What if we chose to, let's say, work in Keldysh formalism? Would it be simpler or more complicated for this particular machinery?
Replica trick is the simplest probably for this.
What would be the key problem with? What would be the key problem with the Keldysh?
With Keldysh,
Yeah.
I don't want my fields to depend on time. I am studying problems without any direction. My fields here, energy is just a single parameter. With Keldysh, you need it to integrate over all energies over long times. I don't need to do it. The denominator. And whatever n is within this range. So n is also the number of terms of action of this subject. So in summation and in the denominator. And it is such that whatever n is, the ratio is always the same. So,
let us thank the speaker. And at 2 p.m. we have to return to our